Okay, great. As I told, my name is Alexander, and first of all, I would like to tell a little bit about our company. Uh, its name is Intellectual Maritime Technologies. We are based in Mykolaiv, that is city in Ukraine, on the Black Sea. Our general activities are software development and engineering calculations. And generally, our team consists of programmers and engineers. We also have a research and development department, and Intellectual Maritime Technologies provides a wide range of engineering calculation of marine propulsion systems such as alignment, vibration, fatigue strength, propeller CFD, and hull structures, finite element method calculations. And our main product is ShaftDesigner software. That is general purpose of that is shaft alignment and vibration calculations. It is based on finite element method and use beam finite element as a basis for all calculations. On the screen you can see the general structure of the software. It consists of several modules. The first one is base model. In this model you create a model of your shafting, and that is the source for all other modules, calculation modules. Then shaft alignment, that has additional part reverse calculation for performing the practical calculation on board of the ship. Then Whirling vibration, that has two modifications for calculating dynamic bending of shaft. Axial vibration module for calculating vibration in the longitudinal direction, and torsional vibration module for estimating rotational vibration of whole propulsion system. And it also has additional transient torsional vibration module. And finally, we also have a special model for fatigue strength calculation that is generally based on two standards, DIN 743 and FKM. And next I will tell you about each of that models a little bit. So the first one, you can see screen of the main window of ShaftDesigner. That is the base model application, and in this model you can easily create shafting model according to the drawings and manufacturer of equipment data. And the workflow in that model is very easy. You can just put necessary elements and objects into your model. It's much easier compared to the general purpose CAD systems. And generally model consists of fixed or controllable pitch propeller, shaft elements, and stern tube, bearings, different type of bearings, crankshaft, gearbox, and so on. And that model that is created in base model is a source for all other calculation, as I told before. So first of all, we need to create base model in ShaftDesigner. Next, the first calculation model is alignment application. It's a model for calculating bending of shafting during shaft alignment procedure and during in different operating conditions. This model takes into account propeller hydrodynamic loads and buoyancy forces of submerged part of shafts and propeller, and it also takes into account bearing length and clearances and hull deflections, thermal expansions of engine bearings, and hydrodynamic lubrication of bearings, and so on. Different acceptance criteria to shaft alignment parameters provided by classification societies or engine manufacturers can be automatically checked in the software when you perform the calculation. And for example, it's bearing loads can be checked, and the misalignment in bearing, and many other acceptance criteria. And that model also has a special tool providing help for engineer to determine the optimal vertical offsets of bearings to fulfill all acceptance criteria and to provide reliable operation of shafting in all operating conditions. This model supports alignment procedures, performing the practical alignment using sag and gap measurements on the decoupled flanges, jack-up tests, strain gauge measurements, and so on. And next module, it's Whirling vibration. It performs calculation of the dynamic bending of shafting, and it calculates dynamic loads acting on the bearings, and that is excited, the dynamic whirling bending excited by the propeller loads, engine cylinder excitation, gear wheel load, and so on. There are two calculations, free and force vibration, and free vibration provides, first of all, Campbell diagram, that is dependence of frequency to the versus speed, rotational speed of the shafting, and you can see there are natural frequencies of shafting, blue lines, blue horizontal lines, and excitation frequencies, that is inclined line, and the intersection between natural frequencies and excitation gives us the resonance points. So for that speed specified on the x-axis, we will have the resonance, and the software provides you help to determine whether that is a dangerous or resonance or not, and to find out the dangerous speeds of shafting rotation. And also free whirling vibration calculation provides mode shapes of free mode shapes of shafting bending. And next calculation that can be provided by Whirling vibration advanced, it's forced vibration, and it is excited by propeller loads and engine cylinder loads and so on. And you can see the dynamic bending. Forced vibration provides all necessary data for analysis, such as deflections and stresses, shear forces, bending moments, and as you can see, there is section orbits, that trajectory of points of the sections of shafting. And we have two modifications of that model. The first one is Whirling vibration basics, that provides only free vibration, free whirling vibration calculation. That is usually enough for class approval to provide documents for classification society. And the second modification is Whirling vibration advanced, that provides all described functionality, including forced vibration, and include damping in the calculation, and that is need for deep analysis of problems that we could find out on board of the ship. And next module, it's axial vibration calculations, and it provides calculation of extension compression vibration of shafting in longitudinal direction. And it also has two types of calculation: free vibration and forced. And free vibration also provides Campbell diagram, like on the previous slide, and also provides free vibration mode shapes, but in this case in longitudinal direction of the shafting. And forced axial vibration calculation provides all necessary parameters for analysis of axial vibration caused by engine cylinder excitation and varying thrust of the propeller. And the results can be shown in different ways. One of the way it's a water flow diagram that provides the overview of vibration amplitudes, vibration parameters. In this case, it's axial load on the thrust bearing, depending on the rotational speed and excitation frequency. And another way to demonstrate the results of calculation, it's a time waveform that provides a varying parameter in time. In this case, this picture demonstrates the axial vibratory displacement of thrust bearing of thrust bearing collar. And the next module, it's a torsional vibration calculation. It provides analysis of the rotational vibration of whole propulsion system, and the whole propulsion system that takes into account in that calculation usually includes propeller, shaftings, and gearbox, engine, flexible coupling, and damper, and some other parts, or electrical motor instead of engine, and so on. This model has its own torsional scheme editor, and it can be used separately from the base model. However, ShaftDesigner provides the possibility to convert base model to the torsional vibration scheme. In this case, base model was used to create that part of torsional vibration scheme that include propeller and shafts. And it also has two calculations, free and forced vibration. Free vibration provides Campbell diagram, and mode shapes, that one of that mode shapes you can see on that picture. And forced vibration provides data of vibratory torque of elements, vibratory stress of elements, gear vibratory torque, power loss in flexible elements such as flexible coupling and damper, and some other parameters. All parameters can be automatically checked according to the latest classification society rules, and at this picture you can see that is stress in crankshaft, and the acceptance criteria provided by the classification society, and you can see that there is a problem because acceptance criteria are not fulfilled. Stress is greater compared to the acceptance criteria, so it provides the data for analysis. And in torsional vibration we also have an additional module for transient calculation that is non-linear. Specifically, it's ice impact torsional vibration due to propeller ice interaction, and short circuit due to malfunction of electrical motor. Next, ShaftDesigner has a powerful reporting system for each of the calculation modules that provides automatical generation of calculation report, and that reports are can be customized. You can include or exclude some data that you need or don't need, and you can change fronts, size, and front, and some other parameters, so it's customizable. And reports for different operating states, different calculations, and different modules can be combined together in one report according to your needs in order that you set. And after that it can be exported to the external file. We support common formats such as PDF, Microsoft Word, HTML and other formats. And we also have a very interesting, powerful feature, Word export template. You can prepare Word template and set it in ShaftDesigner interface, and then all reports that will be exported to the Microsoft Word will be generated with formatting according to that template. So you can prepare that Word template according to the format that is applied in your university, and then all reports will be automatically fit that formatting. So that saves a lot of time. And we also have a very powerful, very flexible licensing. We have different types of cooperation with our customers, and we also have an academic license that are much cheaper compared to the standard version, and but it's only for studying purposes. And also we have a trial version to allow a customer to assess whether they need software or not. We give software for free for usage to try the software to understand whether they need it. And also we provide detailed user manuals for all modules of the software and example projects for all modules that helps to study the software by yourself, and or prepare some teaching materials for students. And on this slide you can see logos of some of our customers. Among our customers there are classification societies, manufacturers of engines, gearboxes, shafts, bearings and propeller, and of course universities. And it's only some of our customers. We have much more customers. And next slide I would like to show a short video demonstrating how to create a base model in our software to give you understanding how it works.
The ShaftDesigner software provides various shafting calculations. This demo shows the example of shafting modeling. Modeling starts by creating a simple shaft element. Then add a fixed or controllable pitch propeller. Add a stern tube. Insert 2 stern tube bearings. Now place intermediate bearing. Insert a flange coupling. Adjust aft stern tube bearing length and position of the forward one. Properties also may be exactly set in the object inspector. Then add a linear layer on the propeller shaft. Change propeller shaft diameter at the aft part. Set number of the propeller blades. Next, insert the gearbox shaft. Replace the flange with the half coupling or joint. And replace the other flange coupling with sleeve or clutch one. Now create engine crankshaft instead of gearbox shaft. Set engine firing order. Add flexible coupling. You can go back to the previous version of the model using the History tab. Adjust the length of the gear shaft. Change type and angle of the gear teeth. Replace journal bearing with rolling bearings. Add the thrust property to the gearbox bearing. Your model is finished and ready for the calculations. Run applications of alignment, whirling, torsional, and axial vibration. Look for more information at the website.
We can finish our discussion. If you will have some other questions, you can email us, and we will be in contact and answer your questions.